Good morning. Today we are going to start with the new chapter, gravitation. Okay, let's come to the Kepler's law of planetary motion. So Kepler studied the Tycho Brahe's data. Tycho Brahe was the physicist who studied the trajectory of planets for whole his life. Okay, he did only one thing. Okay, setting up the telescope, watching the planets, and recording the data. Okay, that was his work. So then Kepler was his assistant. He studied his data. Okay, he also worked along with the Tycho Brahe. Then he was good at mathematics and he formed three laws of planetary motion. Okay, that we are going to study now. All right. So let us study Kepler's laws. So first law is called as law of orbits, and it says that every planet revolves around the sun in an elliptical orbit, not the circular orbit, in an elliptical orbit. So what is an ellipse? So you can say ellipse is an elongated circle. Okay, it looks like this, right? For those who don't know mathematics. Okay, so this is an ellipse. Then there are two foci of ellipse. So now what is focus? So we don't really need to go in all those details, but okay, let's just quickly see what is the focus. So these are supposed two points. These are called as two foci of ellipse. So now if you take some point, okay, if you take any one point, this is one point, let's say point P. So this is F1, this is F2, and you draw these lines from F1 and F2 to the point P. Now there is some distance from first focus, that is F1P, some distance from the second focus F2P. Now you rotate, okay, you move this point in such a way that sum of those two distances are constant. Okay, so then the thing that you get, okay, the locus of all such points in mathematical language, it is known as an ellipse, right? So if you take any one point on an ellipse, then the distance from first focus plus the distance distance from second focus, it is equal, right? Sum of the distances is equal. Okay, so that is an ellipse. So law of orbit says that sun is at one of the foci of ellipse. Okay, foci means plural of focus. So suppose sun is at this focus, then the earth or any other planet, it will revolve in an ellipse. Okay, so this is the first law. So then now we need to know one more thing about an ellipse. So if you join these two foci and draw a straight line passing through those two foci, so then this straight line is known as the major axis of the ellipse. Okay, and if you take half distance of that, see, from this point to this point, it is the major axis. Okay, from A to B. If you take distance from A to O, which is half of AB, that is called as semi major axis. Okay, it's going to come. So then this is law of orbits. It's very simple. Next one is law of areas. Now what is law of areas? So line joining the position of sun to the position of planet, it sweeps out, it moves through equal areas in equal intervals of time. Okay, line joining the position of sun to the position of planet, it sweeps out, that means it moves through equal areas in equal intervals of time. This is the law of areas, Kepler's second law. Okay, so this is law of areas. Now see, if you consider, suppose sun is over here at one of the foci, this is suppose earth, and it moves from point A to B in some time t, then the area covered or area swept out, it's equal to this much, right? This shaded area. Okay, so now suppose at some other time earth is over here and it moves from this point to this point C to D, and this movement is also in the same time, in time t. Okay, then now again some area is swept out, this much is the area, right? So if earth moves from A to B and from C to D in equal time, okay, equal interval of time, then this area and this area, it would be equal. Okay, this area and this area would be equal. This thing is clear? Yes, no? right? So this is an observation. So now see, now what is the significance of this law of areas? Okay, so if you see torque due to the gravitational force, okay, gravitational force acts like this. You can say, you can think of it, okay, the trajectory like a circle. So now the gravitational force will be directed along radius and towards center, or you can say that gravitational force is directed from position of planet to the position of sun, because sun is attracting the planet, right? So at any given time the planet is moving perpendicular to this gravitational force. So if you find out the torque due to the gravitational force, we know torque is what? The cross product of r bar and f bar, that is its magnitude is r times f multiplied by sine theta. Okay, so what is the angle between them? What is the angle between r and f? So suppose this is the planet, this is the position vector of planet from the position of sun. Okay, this is r bar, right? Then what is direction of force? It is opposite to position vector. Okay, so you have r times f multiplied by sine of 180 degrees, because r bar is directed like this. If you think position of sun is the origin, position of planet is given by this position vector r bar, right? Then you have r times f multiplied by sine of 180 degrees, right? Because r bar is directed like this and f bar is directed like this. So this torque would be equal to 0. So if torque is equal to 0, something is conserved. What thing is conserved? We just saw in last chapter. Yes, angular momentum is conserved, right? So this law of areas will turn out to be the law of conservation of angular momentum. Okay, so let's see that. So see, the area covered per unit time is a constant, right? So if you think of, suppose this planet moving from A to B, okay, suppose this is very small angle delta theta, okay, so it moves through very small angle delta theta. Then now this area that it sweeps out, it is approximately a triangle, you can say. And what is area of a triangle? It is half of base into height. Okay, so it's half of this r at time t multiplied by delta s. Delta s is the height, you can say, okay, or distance through which it moves. Okay, so it will be approximately perpendicular, right? If you take very small interval of time, then it will be perpendiculars. Okay, so then delta s and divided by t, delta t. Then what is delta s divided by delta t? So this thing is clear. Delta A means the area covered. It is half of base into height. It is half of r at time t multiplied by height is delta s, right? Okay. Then we are dividing that area covered with time in which that area is covered. Okay, delta t. So delta s divided by delta t. Okay. So why area per unit time? Because this areal velocity would be constant. So Kepler's law is written in this way also, that areal velocity is constant. Why? Because in that way only it will cover equal areas in equal intervals of time. Area covered per unit time should be a constant. Okay. So see, delta s by delta t is V. So you get area covered per unit time is equal to half of r times V, r at time t times V. Okay. If you multiply and divide by m, mass of the object, then what is this thing? So we know that mvr is the angular momentum of planet, okay, around the sun. And then see, mvr we have multiplied and divided by m. So what is constant? L upon 2m is a constant. Okay, L upon 2m is a constant, and that means that angular momentum is conserved as it should be, right? Yes, no? Because torque is 0, so angular momentum has to be conserved, right? The torque is 0, angular momentum has to be conserved. So sometimes they ask this question, that the Newton's Oh, I'm sorry. Newton will come. Sometimes they ask this question that Kepler's law of areas, it is the law of conservation of, so potential energy, kinetic energy, energy, etc., and angular momentum. So what's the answer? It is law of conservation of angular momentum, right? It is the result of law of conservation of angular momentum. So this thing is clear, everyone. Okay, good. Okay, so now not just in this case, suppose if you, even if you take any radial force, that means a planet revolving around sun, electron revolving around the nucleus. Okay, so in that case also what will happen? The angular momentum will be conserved, and we'll see this in the Bohr's model of an electron, that means Bohr's model of an atom. Okay, that angular momentum of an electron remains conserved. So what's the reason for that? This is the reason. Okay, because force is radial, so because force is radial, therefore torque would be equal to what? 0. And since torque is equal to 0, angular momentum will be conserved. And this is the Bohr's postulate, the angular momentum of an electron around the sun, around the nucleus, it is equal to nh divided by 2 pi, and it is constant. Okay, so we'll see that in atoms. Anyways, let's see next one, which is called as law of periods. So what is law of periods? The square of time period of planet's orbit around the sun is directly proportional to the cube of semi-major axis. Okay, so we talked about the semi-major axis. It is the average distance of planet from the sun. Okay, so the square of time period is directly proportional to cube of the radius, you can say. Okay, cube of the semi-major axis means cube of the average distance. Okay, so t square is directly proportional to r cube, is law of periods. So t square is equal to some constant k times r cube, we can say. Okay, so these are Kepler's 3 laws of planetary motion. So are the laws clear, everyone? Okay, good. So then let us see some questions based upon these laws only. So let's see this one. The kinetic energies of a planet in an elliptical orbit around sun at positions A, B and C are Ka, Kb and Kc respectively. So these are kinetic energies at positions A, B and C. AC is the major axis, and SB is perpendicular to AB. This is perpendicular to AB at the position of sun as shown in the figure. Then tell me, anyone, where would be the kinetic energy maximum? Option B, K is greater than Kb is greater than Kc. Why? Okay, so this is a simple question, and this is from NEET 2018. That means it is from NTA. V is high. Good. So since angular momentum is constant, angular momentum L is constant, that means m times Vr is a constant. Okay, so mass is anyway constant, but distance of planet from the sun is going to change. Okay, its maximum over here and its minimum over here. So this v times r is a constant. That means if distance is more, speed would be less, and if distance is less, speed would be more, right? And that's why kinetic energy would be maximum when the planet is closest to the sun. Okay, v is inversely proportional to r, right? Vr is constant means v is inversely proportional to r. So speed is more when distance is less. So at A the speed would be highest, at B it will be lesser than that, and at C the speed would be least. So kinetic energy is highest at A, then slightly lesser at B, and much lesser at point C. Okay, so the option B is the answer. Good, right? So this is simple. Okay, so this is directly from the Kepler's law of planetary motion. Let's see next one. A planet moving along an elliptical orbit is closest to Sun at distance r1 and farthest away at distance r2. If v1 and v2 are the linear velocities at these points respectively, then the ratio v1 divided by v2 is. Tell me. What's the ratio of v1 to v2? Option B. Okay, everyone, is it option B? Right, everyone, that's correct. Okay, good. Since Vr is constant, okay, or MVR is constant, we can say V is inversely proportional to R, and therefore V1 by V2 is equal to R2 by R1. Okay, so that is very simple. Alright, let's see next one. The figure shows elliptical orbit of a planet M around the Sun S. The shaded area SCD is twice. Where is SCD? SCD. Okay, this area, this much area is twice the shaded area SAB. SAB. Okay, this one. Okay, if T1 is the time for the planet to move from C to D and C to D and T2 is the time to move from A to B, then now tell me which one is correct. Option C. T1 is equal to T2. T1 is equal to T2. Why should it be equal? This area SCD, okay, area SCD, this area, it is twice. So option B, right. This area is twice compared to that of this area. Okay, that means since it covers equal areas in equal intervals of time, so if area is double, that means time taken is also double. So time taken to move from C to D must be double as that of what? Time taken to move from A to B. Right, T1 is equal to 2 times T2. Okay, so this one is very simple, right? Okay, so these are basic questions, but this basic question, one of the basic question was asked in 2018. So there might be basic question asked in 2024 also, we don't know, right? Let's see next one. The period of revolution of planet A around the sun is 8 times that of B. The distance of A from the sun is how many times greater than that of B from the sun? Period of revolution of A around the sun is 8 times that of B. Okay, so time period of A is equal to 8 times of time period of B. Then question is, distance of A from B is how many times that of distance of B? Okay, distance of A from sun is how many times? Option A, it might be, let's check. So we have T square is directly proportional to R cube, right? T square is proportional to R cube. That means we want TB, right? We want distance of B. So let's say RB divided by RA, cube of this would be equal to what? TB by TA square. Let's put the values. Okay, so TA is 8 times TB. So TB by TA is 8 times TB. You have square of that. So this will be 1 by 64. And it is cube of something. Right, it is cube of RB by RA cube is 1 by 64. Therefore, RB by RA is equal to cube root of that is 1 by 4, right? And therefore, RB is equal to what? RB is equal to RA divided by 4. Yeah, that's correct. So, RA is equal to 4 times RB. Okay, so that's the answer, option A, right? So again, very simple question. Okay, all right, very good. Let's see next one. So this is, I think, similar. The distance of two planets from Sun are 10 raised to 13 and 10 raised to 12 meter respectively, the ratio of their time periods. Similar to last one, but in that one distance was asked, in this one time period is asked. Okay, so let's say T1 by T2. T1 by T2 square is equal to R1 by R2 cube, and R1 is 10 raised to 13, R2 is 10 raised to 12, you have cube of that. Okay, so that means 10 cube. So this is T1 by T2 square is 10 cube. Take square root of that. So T1 divided by T2 is equal to what? Square root of this thing. Okay, square root of 1000 you can say. That is equal to 100 times 10. Okay, so it's 10 root of 10. Square root of 100 is 10. Okay, and then again some 10 will be remaining, right? So it is option B. So this is also a very simple question, right? It's same as that of last one. Okay, let's see next one. A planet is moving in an elliptical orbit around the sun if T, V, E and L stand respectively for its kinetic energy, gravitational potential energy, total energy and magnitude of angular momentum about the center of force, which of the following is correct? Tell me. T is conserved. T means kinetic energy, which the potential energy is total energy, and L is the angular momentum. Is kinetic energy conserved? Yes, no? No, kinetic energy is not conserved because speed sometimes increases, sometimes decreases. Okay, so this is a good question. So kinetic energy is not conserved. V is always positive. So right now we don't know about, I mean, we haven't studied the potential energy, gravitational potential energy, but let me tell you that gravitational potential energy would be negative, not positive. Okay, the formula for that would be minus of gmm divided by r. Okay, so gravitational potential energy would be negative, so this is also not correct, right? And then E is always negative, so E is always negative is the answer, because this potential energy would be negative and in magnitude it's greater than kinetic energy. Okay, so now see, you remember this thing, for any bound system the energy is always negative. Okay, for a planet revolving around earth, sorry, sun, or earth revolving around sun, or moon revolving around earth, what will happen? The total energy would be negative. Okay, so just remember this, it is going to come. Answer is option C, the energy is always negative. Potential energy is negative, so this one is also incorrect. Let's check last one. L is conserved but the direction of vector L changes continuously. Is this correct? So they say the direction of L changes continuously. No, it's not correct. So what is direction of L? So planet revolves, suppose in this ellipse, what is the direction of L? This is the sun, this is our planet. So see, if you draw its position vector, this is r bar, the position vector of the planet from sun, this is r bar, okay, and at this position v bar would be directed like this, perpendicular to r bar. At this position, this is v bar. If you take cross product of these two, right, so there is this plane in which the planet is revolving, okay, so velocity is in this plane and radius is also in the same plane. Suppose this r bar and this is v bar. If you take cross product of them, then r bar cross v bar will give you what? A vector perpendicular to both of them, that is r bar as well as v bar. So it's along the axis, okay, it is along the axis of revolution, right? So this is L bar, okay, we know in vector product. So this is L bar, which is m times r bar cross v bar, okay. So when we take cross product, the resultant of cross product is perpendicular to first vector as well as the second vector, right? So it is perpendicular to r bar as well as v bar, means it's along the axis, okay. So it's not going to change, right? This thing is clear. And one more thing, see, since torque is 0, if torque is 0 means angular momentum is not going to change, not in magnitude, not in direction, right? Because the torque is 0, okay. So direction of angular momentum also does not change, okay. So this is also incorrect. All right, let's see next one. Two astronauts are floating in gravitational free space after having lost contact with their spaceship. The two they will move towards each other, move away from each other, will become stationary and keep floating at the same distance between them. Tell me. Two astronauts, they are floating in gravitational free space, okay. It's option A. They will move towards each other, move away from each other. Why? Keep floating at the same distance between them. There will be gravitational pull, that's correct. So it will be option A. So see, now I guess you might have got confused that it is gravitational free space. So what does gravitation free space mean? It means that they are far away from any other astronomical body, okay. They are away from stars, very away from other stars, planets, etc. And there is nothing. So suppose we are at some distance away from sun. So sun is pulling us. Us means sun is pulling earth. Okay, if that distance is increased, what will happen? The gravitational pull will be, it will decrease, right? So they are very far away from other astronomical bodies, and you can say that it can be achieved in other way also. Suppose they are surrounded by the stars and planets from all sides, such that the gravitational pull on them due to all other stars and planets, okay, everything else in the universe, it is zero, it is balanced, right? So think of first case, they are very far away from other astronomical bodies, that means stars and planets, okay. So still these are two bodies, right, and there will be gravitational attraction between them, okay. So the distance between them will decrease over the time, okay. So option A is correct. right? Good. Then next, let us see the Newton's universal law of gravity. Okay, so actually this comes from universal law of gravity. So what does the Newton's universal law of gravity say? So it says the same thing, that every body of universe attracts every other body of the universe with a force which is directly proportional to product of masses of two bodies, and it is inversely proportional to the square of distance between them. Okay, every body of the universe, anything, okay, attracts every other body of the universe, right? Then the force between them is directly proportional to what? Product of masses of the two bodies, and it is inversely proportional to square of distance between them. Okay, so if you combine these two, you get force is proportional to m1 m2 divided by r square. And then again, if you remove this sign, proportionality sign, and put an equality sign, a constant will come, that is known as the universal gravitational constant. Why is it known as universal gravitational constant? Because this is universal law, that means it is applicable everywhere in the universe. Okay, so the force of gravitational attraction between us and earth, or we can take any two objects, suppose. Okay, so the force of gravitational attraction between us and earth, or let's say suppose you and some cupboard in your room, there would be gravitational force of attraction between those two, right? So the force of gravitational attraction is given by this formula only. That force is given by this formula. Force of gravitational attraction between earth and us is given by the same formula. Earth and moon, there is some force of gravitational attraction given by the same formula. Then again the moon and sun, you can say, or earth and sun, so gravitational force is given by same formula. So this formula is universal, applicable everywhere, right? Then now this g is equal to what? Fr square divided by m1 m2. If we just move r square on that side, m1 m2 on other side, so we get g is equal to fr square divided by m1 m2. And value of g was not known earlier. It was found by a physicist whose name is Cavendish. Okay, so he did some simple experiment in his lab only, and he found the value of gravity. Okay, you can search about the Cavendish experiment. It's very simple. It's out of our syllabus now. Okay, so we are not going to study about it. So g is equal to 6.67 multiplied by 10 raised to minus 11, and from this formula you can see the unit would be Newton meter square per kg square, right? Newton for force, okay, r square means it is meter square, and divided by m1 m2 means kg square should come, kilogram square. Okay, all right. So now all of these formulae will be given, right? All of the values would be given in the NEET exam, but we should remember this formulae. Okay, I mean we should remember these values also, right, for quick calculations. All right, so this is Newton's law in scalar form, g times m1 m2 upon r square. Then we can write Newton's law in vector form. So there can be a question like this. So Newton's law in vector form can be written like this. Okay, so suppose this kind of diagram is drawn, and this is a body whose mass is m1. This is body whose mass is m2. So masses m1 and m2. They are separated by some distance. So this is our coordinate system. m1 is at position of r1 bar from the origin, m2 is at position of r2 bar from the origin. Okay, then we can say that a vector directed from m1 to m2 is r12 bar. Okay, let's say that vector directed from m1 to m2 is r12 bar. What is that? It is r2 bar minus r1 bar, right? It would be, so see, using triangle law of vectors addition, you can say r1 bar plus r12 bar is equal to r2 bar. Okay, so just take I'm sorry, r1 bar on that side, so we get r12 bar is equal to r2 bar minus r1 bar. Okay, right, this thing is clear. This is very simple, right? Okay, so the force on m2 due to m1, force on m2 due to m1 will it be directed along R12 bar or will it be directed in opposite direction of that? It would be opposite, right? Because if it is along that direction, that means M1 is pushing M2. Okay, actually M1 is pulling M2. Okay, gravitational force is always attractive, right? So that means the force should be directed in opposite direction of R12 bar. Okay, so this is the only question over here. The magnitude will be G times M1 M2 divided by R12 square, or you can also write it as R21 square, because R21 bar and R12 bar will have same magnitude and this is just magnitude. Okay, so this thing is only important here, that in what direction will it be directed. Okay, along R12 bar like this or opposite to that. So it is directed opposite to that, and that's why to show the direction we multiply this thing, the magnitude of force, by a unit vector. Okay, so it is minus of R12 cap, right? So very simple thing, right? It's very simple. Yes, no, Indusha?
Yes, sir.
Okay, good. All right, so let us see some problems based upon the Newton's law. Two spheres of masses small m and capital M are situated in air and the gravitational force between them is F. The space around the masses is now filled with a liquid of specific gravity. 3. The gravitational force will now be. Okay, so let me tell you what is specific gravity. Specific gravity means, does somebody know? Specific gravity is just density of anything divided by density of water. That's it. Okay, so now suppose this is first sphere whose mass is small m, second sphere of mass capital M, and you change the medium between these two. Suppose earlier there was air and now there is this fluid having some density. Okay, will the gravitational force between them change? No change in F, right? No change in F. Very good. So no change in F. That's the answer. Very good. Let's see next one. If the gravitational force between two objects were proportional to 1 by r and not 1 by r square. Okay, so they are asking us to imagine that the gravitational force is proportional to 1 by r and not proportional to 1 by r square, where r is the distance between them. Then the particle in the circular path would have its orbital speed proportional to. Tell me, anyone? So suppose this is a planet revolving around sun. Okay, so that's a planet, this is sun. Okay, the question is orbital speed v is proportional to. Option B, r raised to 0. Okay, very good. All right, so let's see how. So now if planet revolves around sun, then the centripetal force is provided by what? The gravitational force. Okay, so centripetal force is provided by gravitational force, right? So centripetal force is given by mv square divided by r, and if gravitational force is also 1 by r dependent, means it is some constant divided by r, some constant upon r, then what will happen? Video is lagging. Is it lagging for everyone? Yes. Is the video lagging for everyone? No. Okay, good. All right. So you can you can leave and rejoin, right? Okay, so you have mv square upon r is equal to gravitational force, and according to them it's proportional to 1 by r and not 1 by r square. Okay, it's proportional to 1 by r, not 1 by r square. So it is some constant divided by r. So r and r will get constant. So mv square is a constant, means v is constant. So it is independent of r, right? This thing is clear. Okay, very good. So this is also simple question. Let's see next one. The earth mass is given, revolves around the sun, okay, with an angular velocity of 2 multiplied by 10 raised to minus 7 radians per second and a circular orbit of radius this much. The force exerted by sun on the earth in Newton is, tell me. The earth revolves around sun with angular velocity. Angular velocity is given in circular orbit. The force exerted by sun on earth in Newton. Which formula will you use? So see here, the gravitational force provides centripetal force, right? So the force between sun and earth would be equal to, yeah, you can use mv square divided by r, but here the angular velocity is given. Okay, so which formula will you use? FCP equals to mr omega square, right? Because angular velocity is given. Okay, so you have directly this formula mr omega square, and this centripetal force is provided by the gravitational force. That means the gravitational force is equal to what? This thing only, mr omega square, right? It is very simple. So let's just put the values. So mass of earth is 6 multiplied by 10 raised to 24 kgs. Then the radius, radius means not the radius of earth, radius of revolution. Okay, radius of the circular orbit, it's 1.5 multiplied by 10 raised to 8 in kilometers, but then we need to convert it to meters. So 1.5 into 10 raised to 11 multiplied by omega square. So 2 multiplied by 10 raised to minus 7, and you have square of that. So that is, now just do the calculation. So this is 10 raised to 24 plus 11 means 35, and this thing is 10 raised to minus 14, right? So 35 minus 14 is 10 raised to 21, and then multiply this thing. So this will be 4 times 1.5 is 6, 6 times 6 is 36, 36 multiplied by, what was that, 10 raised to 21. Yeah, so that's the answer, option A, right? Okay, so now let us see gravitational force due to a shell. Shell means a hollow sphere. So let's understand this topic. Okay, so suppose there is a small point sized mass m, okay, point object having mass m, and you have this shell. Okay, it has mass, suppose capital M. So then now I want to find out the gravitational force due to this one on this one. So we are not going to find out the force, right? For force we'll say that it is equal to g times m into m divided by r square. R is the distance of this mass from the center. Okay, so see, now if you consider okay, this small mass dm, okay, dm is small part of the shell, small mass over the shell. Then now if you draw a line joining this point, let's say mass m is at point P and O is the center of the shell. So draw a line like this. Okay, then draw a perpendicular from this mass dm on that line. So it meets at some other point. Take again mass equal to this one dm on the other side also. Okay, so then now see this mass m would be attracted by dm. Okay, the mass m, small m, this point sized object, it will be attracted by this mass as well as this mass. Okay, so then gravitational force due to this one is suppose df, gravitational force due to this one is also df, because we have considered two equal masses. Okay, so this one will attract this one with some force, this one will also attract m with the same force, and then you can resolve this force along two components. So if you resolve it along two components, so suppose this angle is theta, so this force is df, then this component would be df sine theta. Okay, and this component would be df cos theta. Similarly for this one would be df cos theta, component through the angle is cos component, component away from angle is sine component, so this one is df sine theta. So you can see that this df sine theta and df sine theta gets cancelled out, and the net force due to this mass and this mass would be what? Along the line joining center of the shell to this point P. Okay, similarly you can consider any mass, any small piece of the shell, let's say over here, then you can draw perpendicular like this. There would be similar mass on the other end also, and the net force due to them would be along this line only. So what is the direction of net force? It is along the line OP, or actually it's directed from P to O. So is this point clear? Yes, no? Okay, so now the net force due to this mass, the shell having mass capital M on this object having mass small m, if it is outside of shell, then it's given by g times m into m divided by r square. Okay, g times m into m divided by r square. Okay, but now this is okay, this is not a surprise, this might not be a surprise, that force between the shell and this mass is what? It is equal to gmm divided by r square. What is r? The distance of this mass from the center of shell. Okay, it is distance of the mass from the center of the shell, right? Now consider a mass, a point sized mass inside of shell. So now what would be the force, the gravitational force due to the shell on this mass? The answer comes out to be equal to 0. Okay, the answer comes out to be equal to 0. Now see how. So see, now consider a small area of the shell on this side. Okay, and then this area will have some mass, let's say dm. Okay, so distance of this small mass from this one is, let's say, r1. Okay, from this area this distance is suppose r1. Now just draw a straight line starting from, or just connect each and every boundary point of this area with this mass and extend those lines to the other end. Okay, if you extend those lines on the other end, you will have this area. Okay, let's call it dA2. Okay, so now there would be some gravitational force due to this dA2 also on mass m, right? And you can notice that we have not considered m at the center. Okay, because if you consider it at center, then you can say, oh, it gets attracted from this side with some force and also from this side, right? The distance is same. Okay, so force would be equal and opposite, so it gets cancelled out. So that is simple, right? If you keep this mass at the center, then it gets attracted from this side with the same force, from this side with the same amount of force. So the forces are equal and opposite from all sides, and that's why they get cancelled out. We have considered that this distance r1 and r2 is different. Okay, so still the net force acting on this m would be equal to 0. Okay, so see how. So now there would be some mass of this area dA1. So if you take surface mass density, sigma is the surface mass density, it is m divided by 4 pi r square. Okay, so total mass divided by total surface area of sphere is 4 pi r square. Therefore, you can write the mass is equal to, the mass of the sphere is equal to sigma multiplied by total surface area. Total surface area is A, right? Then now, what would be mass due to this area? It would be the sigma multiplied by this area only, okay, dA1, right? Then mass due to this area would be sigma multiplied by dA2. Okay, sigma is surface mass density. So mass is equal to surface mass density multiplied by the area. Okay. So then mass due to dA1 is dm1, it is sigma multiplied by dA1. Mass due to dA2 is sigma multiplied by dA2. So force on small m due to dA1 would be just equal to g times m times this dm1 upon r1 square. Okay, and force on m due to dA2 would be g times small m multiplied by mass of the area dA2, okay, divided by r2 square. What is dm2? It is sigma multiplied by dA2. So if you notice, these things are common. G times m times sigma is common in this formula as well as in this formula. That means in both of the forces. Then here you have dA1 divided by r1 square. Here you have dA2 divided by r2 square. And now if you see what is that thing, so this area divided by r1 square gives you what? It gives you solid angle, okay, made by dA1 at the position of m. Okay, if you remember first chapter, solid angle, it is area divided by perpendicular distance square, right? So it is the solid angle made by this dA1 at point m, okay, at the position of mass m. And now you can see clearly these are equal and opposite solid angles, okay, vertically opposite solid angles, so they are equal, right? Not equal and opposite, vertically opposite solid angles, they have to be equal. So dA1 divided by r1 square would be equal to dA2 divided by r2 square, and therefore dA1 upon r1 square is equal to dA2 upon r2 square. So this force F1 is equal to sigma times m into g multiplied by this factor, and this is sigma m into g multiplied by the same factor, right? Because two solid angles are equal, so forces are equal and opposite, okay, because this force will be directed like this one will be directed like this, so the net force will be equal to what? 0. Okay, is this thing clear to everyone? Okay, net force is equal to 0, and now you need to remember this point only. So I have explained it why it is 0, but you need to remember that the net force acting on any mass kept inside a spherical shell would be equal to 0. Net which force? Net gravitational force. Okay, net gravitational force is equal to 0, right? We need to remember this thing. Okay, right? So there can be a direct question based upon this. Okay, there is application of this which we are going to see in some time. Okay, all right. So after that, let us talk about the acceleration due to gravity. So we know that acceleration due to gravity on Earth's surface is equal to what? 9.8 meters per second square, right? G is equal to 9.8 meters per second square. Okay, so we'll discuss various cases of acceleration due to gravity. So first one is at height h above the Earth's surface. Okay, so we know that gravitational force on a mass m due to the Earth is equal to what? Gmm divided by r square. So suppose this mass is m and it is on Earth's surface, then what will be its distance from Earth center? It is equal to r, right? The radius of Earth. Okay, this thing is clear? Yes, no? Okay, so now consider this case. So suppose this mass is at this height h above the Earth's surface. So suppose distance of this m from the center of Earth is equal to r. So what will be this r? It will be radius of earth plus height h, right? Radius of earth plus height h is distance between the center of earth to the position of that mass. Okay, it can be anything, suppose it's a satellite. Okay, so the force is equal to g times mass of earth, which is capital M, mass of this satellite or any object, which is small m, divided by distance square, and this r is equal to what? R plus h. So now we know that weight of the object would be equal to what? It's equal to the gravitational force acting on that object due to earth. So its weight or gravitational force due to earth can be written as m times gh. Okay, m times g, right? Force is what? Mass into acceleration. What is its acceleration? It is gravitational acceleration, and that's why we have written mass times gravitational acceleration, but we have put this suffix h for the height h. Okay, so what is the acceleration due to gravity at that height? It is gh. Okay, so m times gh is the gravitational force, and from other formula, from the Newton's formula, we get g times mm upon r square. This m and m gets cancelled out, and that's why we get g times gh is equal to what? G times m divided by r square. Okay, so that is g times m divided by r plus h square. So acceleration due to gravity at height h above the earth's surface is given by what formula? Gm divided by small r square, or you can say gm divided by r plus h square. Is this thing clear, everyone? Okay, right. So if mass of earth is known, if height is known, then we can find out directly gh is equal to what? Gm divided by r plus h square using this formula. Okay, radius is 6400 kilometers, right? But then that would be a lot of calculation. Okay, so what we do is we relate this acceleration due to gravity at height h to acceleration due to gravity on earth's surface, which would be equal to what? 9.8 meters per second squared, right? So for h equal to 0, that means our object has now come on earth's surface. Okay, object has come down on the earth's surface. So acceleration due to gravity on earth's surface, g is equal to what? Gm divided by h becomes 0 on earth's surface, so gm divided by r square. Okay, so suppose this is equation 1, this is equation number 2, and what you do is you divide equation 1 by 2. Okay, so equation 1 was gh is equal to g at height h is gm upon r plus h square. You divide this equation by that equation, so gh divided by g is equal to gm divided by r plus h square. Okay, we have written down this equation, and dividing by this is multiplied by its reciprocal, so multiplied by r square by gm. Gm and gm gets cancelled out. Okay, so you have gh upon g is equal to r divided by r plus h square of that. Okay, gh upon g is equal to r divided by r plus h square, right? So this thing is clear. Okay, all right, good. So now we need to remember this formula, and this is an exact formula in the sense that we ourselves have not done any approximation. Okay, so there is no approximation in this formula. So gh upon g is equal to what? R divided by r plus h square. So we can use it for any height. Okay, gh upon g is equal to r divided by r plus h square. We can use this formula for any height, okay, above the earth's surface. All right, then now let's do some approximation. So for that, what we do is we divide this numerator and denominator of this thing by by r. So divide it by r, or what you can do is you can take r common from the denominator. So what remains is, from this r 1 will remain, okay, and you have taken r common, that means So you have h only here, you don't have r. So when you move r out, that means you need to divide by r also. Okay, because if you multiply by this r, you will get r times rh by r, that r will get cancelled out and you will get this h. Okay, all right, so this r gets cancelled out. So you have 1 upon 1 plus h upon r square, 1 divided by 1 plus h by r square, and which can be written as 1 plus h by r raised to minus 2. So gh is equal to g multiplied by 1 plus h by r raised to minus 2. Okay, is it clear till this point? Right? Okay. After that, what we do is we need to find out that this 1 plus h upon r raised to minus 2, what is this thing? So what we do is we consider the case where h is very small compared to r. Okay, h is very small compared to r, means h upon r would be very small, and then we make use of something which is known as binomial expansion. Okay, what is binomial expansion? If you have 1 plus x raised to n, then it is given by, okay, it is expanded as 1 plus nx raised to 1, then you have n times n minus 1 upon 2 factorial x raised to minus 2, sorry, x raised to 2, plus so on and so forth up to plus x raised to n. Okay, all right, so here see, what is your x? X is equal to h by r. What is your x? X is equal to h by r. So then if you expand it, what will be your n? So n is equal to minus 2. N is equal to what? Minus 2. So you expand this. Okay, so what do you get? Gh is equal to g multiplied by 1 plus, right, you have 1 plus n times x. Okay, so that is minus 2 times, because your power is minus 2, so n is minus 2, minus 2 times x, which is h by r, plus minus 2 times minus 3 divided by 2 factorial, okay, h by r square, plus you will get higher power terms for h upon r. That means in next term h by r raised to 3 will be there, in next to next term there will be h by r raised to 4, so on and so forth, right? So now if h is very small compared to r, so this is our approximation that h is very small compared to r, and what we can do is we can neglect all the higher power terms, because if h is very small compared to r, h square will be very small compared to r square, and that's why all the higher power terms are neglected, and what remains is 1 minus 2 times h by r only. So gh is equal to g times 1 minus 2h divided by r. Okay, so is this thing clear? Yes, no? Right, now you have got two formulae. Okay, two formulas for gh. One is g times r upon r plus h square, this is one formula, and another one is g times 1 minus 2h upon r. So when should you use which formula? Okay, which formula is to be used when? This is the question. So if h is very small compared to r, use this formula. If h is comparable with r, that means if they say that h is equal to r by 2, which formula should you use? You should use this formula. Okay, if they say h is equal to r by 4, still you should use this formula only, right? So this formula you can use approximately. Okay, if h is about 10% of r, 10% is also very high, but in NEET we don't have that much time, right? So what we can do is, so even if it is suppose 640 kilometers and r is 6400, right? So you can make use of this formula and you will get roughly about the same value. Okay, it will be little bit different. Okay, but then you can use this formula. Up to 5% it will be very accurate. Okay, so see, roughly if h is given in terms of r, if they say that h is equal to r by something, or 2r or 5r, then don't use this one, use this formula. And if h is given like h is 50 kilometers, h is 100 kilometers, okay, 200 kilometers, make use of this formula, right? This thing is clear? Yes, no, everyone? Okay, good. All right, then let's talk about the acceleration due to gravity at depth d. Okay, we talked about acceleration due to gravity at some height h. Height is also known as altitude. Okay, then acceleration due to gravity at some depth d below the earth's surface. Okay, so now we know that g is equal to gm upon r square is the formula for acceleration due to gravity on the earth's surface, right? G is equal to gm divided by r square. And now suppose that rho is mean density of earth. Mean means average density. It's not like the density of earth would be same everywhere, but we are taking an average value for the density. So average value is suppose rho. Rho is the average density of earth. Then we know that density is mass upon volume. So mass can be written as density times volume. So mass can be written as what? Rho multiplied by 4 by 3 pi r cube. You just put that over here. When you put that in this formula, then you get g is equal to g by r square, and for m you have put density multiplied by volume. So it is density multiplied by 4 by 3 pi r cube. Okay, then you do some simplification. What simplification? You just divide this r cube by r square, so r will remain. Okay, r will be left, and then you get what? G is equal to 4 by 3 pi r rho g. Okay, small g is equal to 4 by 3 pi r rho g is the formula. Okay, in terms of density. This thing is clear? Yes, no? All right, very good. So this is acceleration due to gravity on surface of earth in terms of density. Okay, so you have this formula. Then now suppose you dig a well, okay, having depth d, and you go to the bottom of that well. So then what would be acceleration due to gravity at depth d, right, at the bottom of that well? What would be the acceleration due to gravity that we want to find out? So for that, what we do is, see, we have already seen that if you consider a spherical shell like this, what is acceleration due to gravity? What is the gravitational force due to that shell? If you have some mass over here, it is 0, right? Yes, no? Okay, so you can consider the shell of this much thickness. So due to this shell, this is this outer shell, due to this outer shell, there will be no gravitational force at this point. Okay, that means no gravitational acceleration. So the gravitational acceleration at that point would be just because of the sphere of radius r minus d. Okay, gravitational acceleration at this point would be just because of the sphere of radius r minus d. So there is nothing difficult in that. So the acceleration, gravitational acceleration at depth d, let's call it g suffix d, it is because of this sphere having radius r minus d. So on the surface of earth, it is because of this sphere whose radius is r, and it was, the formula is 4 by 3 pi r rho g. Okay, so just change r to r minus d. So just do that. So acceleration due to gravity at depth d is equal to 4 by 3 pi multiplied by radius of that sphere, which is r minus d, times rho into g. Okay, same formula. In place of r, we have substituted r minus d. So again, let's call this equation 1. This is equation 2. Divide 2 by 1. So dividing 2 by 1, what do you get? 4 by 3 pi r minus d rho g divided by 4 by 3 pi r rho g 4 by 3 pi and 4 by 3 pi gets cancelled out, rho g gets cancelled out, and you have r minus d divided by r. Okay, so move g on other side. Okay, so r upon r is 1, so you have 1 minus d divided by r. Okay, so g at depth d is g times 1 minus d upon r. Is this thing clear? Is this formula clear, everyone? Now where is it applicable? Up to what depth would it be applicable? All depths, right? Is there any approximation in this one? Is there any approximation in this one? There is a little approximation, not little, actually it's a big approximation, that rho is mean density of earth. And now see, when you see, composition of earth is different. Okay, so what is the composition of this core? Will not be composition of outer layers. So mean density here and mean density here will not be equal, right? If you consider mean density of this much part and mean density of this part, it would be different, but we are considering it to be same. That is the approximation, okay, which is not correct, of course, but now we need to do something, right? Okay, so there is an approximation, but you can use this formula for all depths. Okay, right. So then now if we want to plot this acceleration due to gravity versus distance from center of earth, how will the plot look like? Okay, what will be the formula? So first here you can see g at depth d, okay, can be also written as g at distance r from the center of earth. And what will be this r? It is just equal to r minus d. So g at distance r from the center can be written as what? 4 by 3 pi, and in place of r minus d you will have small r. What is small r? It is distance of that point from the center of earth, which is r minus d. So you are replacing r minus d with r. Okay, the same formula can be used, okay, till what? Till when? Till you reach the surface of earth. Same formula can be used, 4 by 3 pi, okay, 4 by 3 pi multiplied by r rho g, right? This thing is clear? Yes, no? Okay, so from the center of earth till the surface of earth you can make use of this formula, 4 by 3 pi r rho g. R is distance of the point from the center of earth, okay, and then 4 by 3 pi is a constant, rho and g is a constant. We are assuming rho to be constant, okay, so gr will be directly proportional to r, right? Acceleration due to gravity at distance r from the center would be directly proportional to r. Till when can you use this formula? Till you reach the surface of earth. That means small r becomes equal to the capital R. Okay, till then you can make use of this formula. After that, what happens? After that we need to make use of this one, gh is equal to g times capital R by r square. So capital R is a radius of earth that is constant. Let's take it as a constant. So g is a constant which is 9.8. That means gh is inversely proportional to r square. So gh is inversely proportional to r square. That means the acceleration due to gravity will fall off like this, inversely to r square. Okay, so where is it maximum? On the surface of earth the acceleration due to gravity is maximum. Okay, so from the center till surface it is linear, the graph is linear, that means it is directly proportional to r, and from surface onwards, okay, from the surface of earth for any outside point it is inversely proportional to r square. Is this graph clear, everyone? Okay, so then there is one small concept called as gravitational field. So what is gravitational field? It is just gravitational force per unit mass. Means it is acceleration due to gravity only. Right? What is gravitational field? So suppose you have this mass over here and gravitational force acting on that mass due to all other masses, all other small point sized objects, you can say. You can add up all those forces. Okay, so what would be gravitational field at that point in space? It is just sum of all those forces, means the net gravitational force acting on this mass divided by the mass itself. Okay, so what is this actually? Total force per unit mass means it is just acceleration of this mass. This thing is clear. If there is no other force, then there would be only gravitational force. Okay, suppose there is only gravitational force, then what is gravitational field? It is just sum of all the gravitational forces acting on this mass divided by the mass. So force upon mass is what? It is acceleration. This thing is clear. Okay, then the gravitational field due to earth. What is gravitational field due to earth? So it is just gravitational acceleration of earth, or not earth, of an object due to the earth, due to the gravitational force of earth. Okay, so what is gravitational field? Again, gravitational force. So suppose you have this mass m. What is gravitational field of earth? So gravitational force acting on this mass, gmm divided by r square, divided by that mass itself. So the mass gets cancelled out. What you are left with is gm divided by r square, and you know that it is the gravitational acceleration, okay, due to the earth. This thing is clear? Yes, no? Right? Good. Then, okay, so what will be gravitational field inside a spherical shell? What would be gravitational field inside a spherical shell? Zero. Right, it is zero. Zero. Exactly. Okay, so gravitational field is zero because the gravitational force inside a spherical shell is zero. Okay, now answer this question. Which one of the following plots represents the variation of gravitational field on a particle with distance r due to thin spherical shell of radius capital R? Okay, tell me, r is measured from the center of spherical shell. So option A, option B, B, right. So option B is correct. Yeah. So is everyone convinced with this one? Because inside shell the gravitational force is zero. Okay, so gravitational field is zero, and outside of it, it's inversely proportional to r square. Okay, good. So this is the answer, right? Okay, good. Let's see next question. A body of weight 72 Newton moves from the surface of Earth at height half of the radius of Earth. Okay, the body moves till half of the radius of Earth above the surface of Earth, right? It's the height. Then the gravitational force exerted on it will be. So very simple. What will be the gravitational force? It will be equal to just its mass times gh, and what's given, that this is force at height h. What is given? Its weight on the earth surface. Okay, so weight is what? M times g only, right? Mass times acceleration due to gravity on earth surface, that is 72 Newton. This is given. Mg is equal to what? 72 Newtons. And you want to find what will be gravitational force on it. That means its weight only, but at height h. Okay, this is simple, right? Yes, no? Okay, it is simple. It is just g multiplied by Which formula will you use? Tell me. 1 minus twice h upon r, or r divided by r plus h square? Height is equal to h is equal to r by 2. Which formula will you use? So see here, if you make use of this one, gh is equal to, yeah, r upon r plus h square. You will use that formula. Gh is equal to, if you use g times 1 minus twice h upon r, so put h is equal to r by 2 and see what do you get. Okay, 2 times of r by 2 by r. What is this thing? R divided by r is 1. So 1 minus 1 is 0. So this formula is giving you horrible result, right? It's saying that acceleration due to gravity at the radius is equal to, sorry, height is equal to r by 2. It is 0. Means if there is an object, okay, which is at distance of r by 2 from Earth's surface, it will not be attracted by Earth. Okay, so which is not at all correct, right? Okay, so this formula gives you horribly wrong result for large heights like this. Okay, so we'll use not 1 minus twice h upon r. Option B, let's check, r divided by r plus h square. So you have mg is equal to 72 newtons, and what is r divided by r plus h? R plus r by 2, right? And you have square of that. This is, r will get cancelled out everywhere. This is 1 plus half, means 3 by 2. So 3 by 2 in denominator means you have 2 by 3 and square of that. 72 times 4 by 9, right? 2 by 3 square. Okay, 32. Yeah, it's correct. Option B. Okay, so simple question. Very, very simple, right? Okay, good. Let's see next one. This is from NEET 2018. If the mass of sun were 10 times smaller, okay, mass of sun, let's say mass of sun prime is equal to 10 times smaller, means right now the mass of sun is suppose ms divided by 10, and the universal gravitational constant were 10 times larger in magnitude. So suppose they say that universal gravitational constant is made 10 times larger. Okay, then which one of the following is not correct? Which one of the following is not correct? Okay, tell me. Raindrops will fall faster. Raindrops will fall faster. Is it correct? Not correct? Walking on ground would become more difficult. Option D, let's check. Time period of simple pendulum on Earth would decrease and G on Earth will not change. Okay, so Vishalini said it's option D, G on Earth will not change. Okay, this is incorrect, right? That's what is asked, which is not correct. So it's option D, that's correct. I mean, your answer is correct, right? So G on Earth will not change is incorrect. Why? Because G is equal to Gm upon R square. Okay, so G dash will be equal to what? Capital G dash, capital G prime times m upon R square. This is not mass of Earth. Mass of Earth is not changing, right? So we'll keep mass of Earth to be same. So G will become 10 times. Okay, 10 times of 9.8. And therefore raindrops will fall faster because Earth will attract them with higher force. Then walking on Earth would become difficult because the acceleration due to gravity is much more. So Earth will not let us lift our legs for walking. Time period of simple pendulum would decrease, So time period of simple pendulum, it's given by this formula, t is equal to 2 pi square root of L by G. We had seen this in the first chapter, right? It will come again in oscillations, but it's inversely proportional to root of G. So if G is increased, means time period would decrease. So that is also correct. What is not correct? G on earth will not change. Okay, actually it's changing, right? So everyone, is it clear? Okay, good. So this is from 2018, means NTA question. Okay, good question, right? Let's see next one. A spherical planet has mass m suffix p and diameter d suffix p. A particle of mass m falling freely near the surface of this planet will experience acceleration due to gravity equal to. Okay, so this is nothing. G acceleration due to gravity is just gm divided by r square, and in place of r they have given diameter, so just put d is equal to 2r, or r is equal to d by 2. Option A. Okay, maybe option A. So r is equal to d by 2. If you substitute, then you get gm divided by r is d by 2. You have square of that. Yeah, that 4 will go in numerator. So 4 times gm divided by d square. So very simple question, and it was asked in 2012. So I don't think there is any relation of the year in which the question is asked. Okay, because this question is better, slightly better compared to this one, right? Anyways, all right, so very simple question. Let's see next one. Imagine a new planet. Okay, we can imagine anything in physics. Okay, this is just imagination. I mean, if you see this question, g dash is equal to g prime is equal to 10 times g. It's given in the question. If you change it, not like this, even if you change it 1%, no, so all life in the universe will vanish. Okay, you can search that. If g is changed even for 1%, even if there is 1% change in capital G, means universal gravitational constant, okay, the world will not be same, the world will collapse. But we can imagine anything in questions, physics questions, right? Imagine a new planet having same density as that of Earth but 3 times bigger than Earth in size. This is possible. Okay, so same density as that of Earth. This planet has density of planet is same as that of density of Earth, but it is 3 times bigger. But radius of planet is 3 times of radius of Earth. Option D. Let's check. Then if the acceleration due to gravity on Earth's surface is g, then on the surface of new planet is g dash, g prime, then what would be g prime? Okay, so which formula will you use? In terms of density, right? G is equal to 4 by 3 pi r rho g. Make use of this one, right? G is equal to 4 by 3 pi r rho g. Very good. So g prime would be equal to 4 by 3 pi r prime rho g, and r prime is equal to 3 times of r. Density is equal. Okay, so density is equal, right? So that means 4 by 3 pi times 3r into rho g. So this is just 3 times of g. It's very simple question, right, from 2005. So that's why we need to remember this formula. Okay, we need to remember. So this is an intermediate step in calculating acceleration due to gravity at depth d, but we need to remember this formula because they can ask questions like this, right? Okay, very simple. Let's see next one. The density of newly discovered planet is twice that of Earth. Very good. Density of planet is 2 times the density of Earth. Then the acceleration due to gravity at the surface of planet is equal to that of surface of Earth. So Gp is equal to acceleration due to gravity on surface of Earth, that means G. If the radius of Earth is r, the radius of planet would be. Again, let's make use of that formula. So Gp is equal to G. This is given. That means 4 by 3 pi. Okay, you can forget 4 by 3 pi also. I mean, we need to compare these two, no? So 4 by 3 pi, radius of planet, density of planet into G is equal to 4 by 3 pi r rho G. Okay, option D, let's check. So 4 by 3 pi, 4 by 3 pi cancelled, G cancelled. Okay, and you want radius of planet, so take density of planet on that side, or density of planet you can put here itself. So 2 times density of Earth is equal to r times rho. This is radius of planet. Density of planet is 2 times density of Earth. So rho cancelled, take 2 on that side, right? So it is equal to radius of planet is radius of Earth divided by 2. So it is option D. That's correct. Okay, so similar question. Very simple, right? Okay, let's see next one. The acceleration due to gravity on planet A is 9 times the acceleration due to gravity on planet B. A man jumps to height 2 meters on surface of A. What is the height of jump by the same person on the planet B? Tell me. Man jumps to the height of 2 meters on surface of A. Then what would be the height of jump on surface of B? Okay, so here suppose man jumps with certain velocity. So we need to assume that that velocity must be equal in both cases, right? So velocity, or let's say speed of jump, is equal. Then it becomes very simple. Okay, speed of jump is equal, means kinetic energy is equal, and the kinetic energy on the surface of the planet is equal to potential energy at height h, you can say, right? Potential energy at height h. Okay, therefore mgh would be equal. So let's say mg at a, h at a is equal to m times g at b, h at b. So gets cancelled. Okay, and therefore what do you have? You have jump at a, it jumps to 2 meters, and acceleration due to gravity of a is 9 times, ga is equal to 9 times of that of gb. So we can cancel out ga and gb also. So ga is 9 times of gb, right? You have gb multiplied by h at b. Sorry. So this thing gb and gb gets cancelled out. You want height at a, so move that 9 on that side. No, we have height at a, right? Man jumps to height of 2 meter at a, so put that 2 times 9 is 18. So h at b would be equal to 18 meters. That's the answer. Okay, simple. Right, let's see next one. What will be the formula of mass of the earth in terms of g, r and g? So this is very simple. You know that g is equal to gm upon r square. Okay, and therefore mass of earth is equal to g multiplied by r square divided by g. This is very old question, but then when they ask this, yeah, it will click, right? Okay, click very quickly. So g r square by g, option B, that's the answer. Okay, let's see next one. The acceleration due to gravity g and the mean density of earth rho are related by which of the following relations? So yeah, rho and g, they are related by which relation? So we know that g is equal to 4 by 3 pi r rho g, and we want rho, so it will be 3 by 4 times g divided by what is left, pi r g. Okay, pi r g, no, pi, yeah, pi r g. So 4 pi r g, option A is correct. So I don't think they will ask this, but we don't know. Okay, let's see next one. The radius of earth. Okay, the radius of earth is about 6,400 kilometers and that of Mars is 3,200 kilometers. The mass of earth is about 10 times mass of Mars, and object weighs 200 Newton on the surface of earth. Its weight on the surface of Mars will be. Okay, tell me. There can be a question like this, comparison based. Okay, so the radius of earth is 6,400 kilometers and that of Mars is 3,200 kilometers. Mass of earth is about 10 times the mass of Mars. So we just need to find out acceleration due to gravity on Mars. Let's call it planet. Okay, Mars, a planet. So you have g times mass of planet divided by radius of planet square, and put what is m and r. M and r is given, no? An object weighs 200 Newton on surface of earth. Okay, that's fine. So mass of earth is 10 times the mass of Mars. So mass of Mars, so mass of planet is m by 10, right? So you have g times m divided by 10 upon radius of Mars is r by 2, half of that of earth. So then this is r by 2 square, so that 4 will come in the numerator and this 10 goes to the denominator. You have gm divided by r square. So 4 by 10 means 2 by 5. Okay, so it is 2/5 of g, and therefore weight on that planet would be equal to what? It is 2/5 on of the weight on earth, so that is 2 by 5 weight of the object on earth, 2/5 of that, that's 200. 200 times 2 is 400 divided by 5. How much? 80. Right? So 80 Newton is the answer. Okay, this one is clear. Okay. All right. So this part is simple. Okay, it doesn't mean that what we are going to see tomorrow is not simple. It is also simple, but this is basic, and there have been questions asked on this thing also, but more questions will be asked based upon the part that we are going to see tomorrow. Okay, more questions are asked these days based upon that. Okay, so gravitation is very simple chapter, right? So if you do that, at least there will be one question. Okay, minimum one question based upon this one. So that one question, it is like it should be fixed. Okay, all right, so I will share the homework based on gravitation, and I will say which questions to be solved. Please do that. And if you have not attempted the test, okay, please do that. The test is based on work, energy and power, right? So solve the test please and tell me